So this lesson's all about the physical structure of the sine and cosine function. And as you can see, that's basically our only goal, is to sketch one single period of the sine and cosine function. And I'll go over what a period of a sine and cosine function is if you don't already know. Now, for most students, the sine and cosine function will probably be the first unique function of its kind, in that it's not like a quadratic or a rational function or a parabola where when you graph it, that's it, you're done, because the sine and cosine function exhibit a particular behavior. What is that behavior? Well, I think it's easiest to see if we just take a look at the parent function. So if you were to go use a graphing calculator Desmos and say graph sine, you can see this is the picture that we get. A whole bunch of oscillations, a whole bunch of waves, a whole bunch of up and down motions. And I can probably drag this on to forever to the right, and hopefully we can see that it just keeps repeating. And cosine is going to be the same way. Cosine just keeps repeating. So for most students, trig functions are the first functions, are the first periodic functions that they will ever encounter. Right? So that's sort of the idea behind things. Sine and cosine are called periodic functions. And it's most likely the first function, the first periodic function students will face. Sine and cosine are called periodic functions. That is to say, they repeat a base pattern over and over. So that's the definition of a periodic function. It's just a function or a graph that sort of has like a template, has a basic structure that just keeps cycling over and over and over again. So what would be the basic cycle? Now for the sine function, I mean, we can pick whatever we want to be the basic cycle or the basic picture, but obviously it sort of makes sense that most people want to start the function at 0. So if I were to say, you know what, this is my starting point, what would be the basic shape? Well, let's just keep tracing out the graph until we find ourselves repeating the structure. So starting at the origin here, we notice that the graph goes up until we hit this point, goes back down until we hit this point here, keeps going down until we get this point, and then it goes back up until we hit this point. So this sort of up and down motion, for sine at least, seems to be like the single picture, the single shape that gets repeated. So for the sort of like the parent function, for sine at least, looks like it has this shape. And we can, Desmos sort of tells us the points exactly. We can be a little bit accurate here. It looks like we go from 0 to pi halves to pi, 3 pi halves to 2 pi. So we saw that the maximum here was 1. The minimum here was -1. This was 0. This was sort of pi halves. Obviously, my drawing's not to scale. This is pi. This is 3 pi halves. And finally, this was 2 pi. So that what we've drawn here is one cycle. I mean, if I wanted to continue on the shape here, I could have continued on, but I'm just going to draw one cycle. Now, what about, so this was for y equals sine of x. Now, what seems to be the general pattern or basic shape for the cosine function? Again, we can start looking any way we want, but sort of looking at the origin, looking at x equals 0 seems a normal starting point. So at x equals 0, we can see for the cosine function, it actually starts all the way up here. Then as we move rightwards, we hit this point, keep going rightwards, we hit this point, keep going rightwards, we hit this point, keep going rightwards, we hit this point. Now, if I were to continue going, I notice I'm just repeating this up and down, down and up motion. So at least for the cosine function, this seems to be the basic shape. Starting at the top, going all the way down, and then going all the way back up. Because if I were to keep going again, I'm just repeating this down motion, and up motion, down motion, and up motion. So in terms of what is the most basic shape, or what is one particular cycle, this seems to be it. Oops, lost my points. This seems to be it for cosine. So we'll go ahead and just sketch that in our graphs here. So for cosine, it doesn't seem to start at the origin. It actually starts at the top here. But if you notice, if you look at the graph, the maximum, the very, very top, has a y value of 1, and the minimum, the very, very bottom, has a y value of -1, so at least that part's still the same, 1 and -1. The only difference is, for the cosine function, we start at the top, and then go all the way down, and then go all the way back up again. So that seems to be like the one cycle of the cosine function. And again, if we look at the x values, it looks like it has the same segments. X equals 0, x equals pi halves, x equals pi, 3 pi halves, and then finally 2 pi. So this is 0, not drawn a scale. This would be pi halves. This would be pi. This would be 3 pi halves. Then up here would be 2 pi. So this would be the parent function of the cosine function. So again, as I said, the above graphs represent one period of the sine and cosine function. If we were to extend the graphs to the left and to the right, as we saw in Desmos, we would just see this shape going on forever, forever, forever. Notice how both the sine and cosine function, they look similar. Right now I'm showing the cosine function, but here's the sine function. Here's the cosine function. Here's the sine function again. They basically have the same shape. I mean, let's put both graphs on at the same time. You can see that with the exception of one being slightly shifted or off center, they're basically the same function. So because sine and cosine, I mean, technically we treat them as two separate functions, but since sine and cosine look so familiar, in fact, I would even go beyond saying that they look very similar. I would say they look identical. They are identical, except just shifted a little bit. We call both shapes or graphs sinusoidal, right? So in the math world, we would say that this shape here is a sinusoidal shape, and this shape here is a sinusoidal shape. Well, with these special, I'm putting special in quotes even though you can't see it, with these special shapes called sinusoidal waves, there are parts to them, vocabulary words that we should probably talk about. So let's just draw a generic sinusoidal wave. In a sinusoidal wave, let's just draw a sine function. Doesn't really matter. It could have been cosine. Look, something like that. There are particular parts of vocab words that we need to address. So let's deal with the obvious. All these sinusoidal waves have like these very, very top points. Not surprisingly, we call that the maximum point. All of these sinusoidal waves sort of have these bottom points. Not surprisingly, we call them the minimum. And you guys notice how, like, on the sinusoidal wave, it is a wave. It sort of goes up and down, back and forth, back and forth. It seems to be sort of like going back and forth, between a particular midline, between a middle point. Well, that midline in this particular example, or in this particular sketch, the x-axis, that midline is what we call the, well, this guy has like many, many names. So you can call him the principal axis, or the sinusoidal axis, or sometimes I get lazy, I just call it the equilibrium line. I will admit the first two terms is more official, it's more sophisticated. That last term is not as sophisticated, but it's the one I use the most often because it, it sort of makes sense. It's the line that sort of balances everything. Now, if you look at the equilibrium line or the sinusoidal axis, you should know that the graph itself is a certain distance away at any given point from the equilibrium line. Well, the distance from the sinusoidal axis to the maximum or the minimum, they should be the same. Even if my picture doesn't make it look like it, they should be the same. We call that the amplitude of the function, right? So the amplitude is sort of like the biggest distance away the graph can go from the equilibrium line. Now, we did say that these graphs here go on forever, 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 forever. Well, the horizontal length, you can sort of think as the, quote, time it takes for the graph to produce one picture. So I drew a sine graph here, and what did we say was one basic shape of the sine function? This was the basic shape of the sine function because the whole wave is just this shape repeated over and over and over again. Well, the horizontal length needed to make that one shape, so this is the horizontal length needed to make this one shape here, this is what we call the period. So the period of a function is the horizontal length, the amount of angles needed to produce one full picture of your function. That is the definition of a period. Now, okay, graphing the basic shape, the parent function should be easy. I mean, we already did it right here, right? 0, 0, pi halves 1s, pi 0, 3 pi halves -1, and 2 pi comma 0. So these points are easy to find. Same thing with the cosine function. Now 0, 1, pi halves 0, pi -1, 3 pi halves 0, and 2 pi 1. Well, how do I graph more complicated functions, right? How do I graph, if there's multiplication, division, adding, subtracting? Well, as I said many, many times in previous units, I don't care if we're talking about simple functions like lines or quadratics. I don't care if we're talking about complicated functions like rationals, square roots, or even these trig functions. Every single functions are controlled or dictated by function transformations. So you know what's coming. You've seen this chart before, but it's worth writing again and again and again. So we should know for any given function, if we add to it, it moves the graph up. For any function, if you subtract from it, it moves the graph down. For any function, if we add straight to the x, we move it to the left. For any function, we subtract from the x, we move it to the right. For any function, when we multiply to the whole function, we vertically scale it by whatever it is you multiply. For any function, when you multiply directly to the x, you horizontally scale it by the reciprocal. So anything that happens to the x is sort of backwards. If you make the whole function negative, it's a reflection over the x-axis. And if you multiply just the x by a negative, it's a reflection over the y-axis, right? So when it comes to sketching more, quote, complicated sines and cosine functions, we have to follow these rules because that's what happens. So in the context of a sinusoidal wave in the context of a periodic function, each part changes at a physical attribute, the amplitude, the principal axis, so on and so forth. Each part changes a physical characteristics, and how do they? This is how they change it. So the general sine and cosine function. So the idea is that all sine cosine functions can be written in the form y equals some coefficient a sine of, now I'm using sine, you can easily replace that with cosine, it really doesn't matter, b times the quantity x minus c plus d, right? So here's the basic trig function, sine of x, but there are lots of things you can do to it. You can add stuff to the outside, you can add or subtract directly to the x, you can directly multiply the x, or you can multiply the whole function. And again, each of these pieces will change a physical attribute or a physical characteristic of the graph. How so? Well, let's just start labeling. The easiest one is the a here. Anything that you multiply the whole function by, that's going to change the amplitude. Right. The next easy one is this plus d on the outside here. Anything you add or subtract to the outside of the function, that's going to change your principal axis, or your equilibrium line, or your sinusoidal axis, whatever you want to call it. Specifically, your principal axis or your sinusoidal line will always be y equals whatever that number is. Now the c here, whatever you're adding, subtracting to the x, remember in regular functions that just moves things to the left and to the right, so there you go. This c will still control moving to the left or moving to the right. However, in the context of trig, we don't call it a translation, instead we call it a phase shift, which again is just a fancy way of saying moving to the left or moving to the right. Lastly, the more difficult concept, the b here. The b will affect the period. It affects the, quote, time it takes from one full picture to emerge. Now remember how we said that anything that happens to the x is sort of backwards? When you multiply directly to the x, it's actually sort of a reciprocal nature. So the new period of your function will be 2 pi divided by b, divided by whatever you scale it by. Now why is it 2 pi divided by b? Well, we saw before in the parent function, it takes exactly 2 pi radians for a complete picture. So here's the complete picture for the sine function. It took 2 pi radians. Here's the complete picture for the cosine function. It took 2 pi radians. So that's why the new period is always based upon 2 pi. And then, of course, you'll just scale it by whatever that b value is. So what are my expectations for you guys when it comes to sketching? My expectation is that, I'm not going to expect you to break out trig paper every single time you sketch. I just want a quick, not doodle, somewhere in between a doodle and a computer-generated graph. I just want you guys to have the correct shape and sort of the correct period and breakdown. So just like with anything, let's just go ahead and sketch using just function transformations. I only want you to transform certain points. What certain points am I looking for? Well, let's recall the parent functions. For sine, we saw that, I guess I could just copy and paste from the above, but I'm lazy and I don't feel like scrolling all up over again, so we'll just redraw it. We saw sine having this sort of shape. And we saw that, at least on Desmos, these were the nice, easy points to figure out. At 0, at pi halves, at pi, 3 pi halves, and then 2 pi, right? And the maximum was 1, and minimum was -1. These are the 5 points I'll be looking for. These are the 5 points that we need to transform. And then for cosine, we saw it sort of started on top, went to the bottom, and then went back on top again. So again, starts at 0, pi halves, pi, 3 pi halves, and then finally 2 pi, right? Max of 1, minimum of -1. And again, Desmos sort of naturally broke apart this graph into these 5 points as well. So these are the 5 points that I'll be looking for that you shifted properly. Now that seems like a lot of work. Oh my goodness, Mr. Foe, you're telling me I have to shift all 5 points, do the function transformations 5 times for every single graph? No, because you should notice that sinusoidal waves, these periodic functions, they are predictable. So if you just understand what the pattern is, you can sort of like shift all 5 points at once. So what is the pattern that we notice for the sine function? Well, what are the 5 special points? These 5 points here. Now they are all special. How? This point here starts at the equilibrium, starts at 0. This point here goes to a maximum. This point here goes to the equilibrium. This point here is a minimum. This point here is an equilibrium. So that's sort of the pattern that I say in my mind when it comes to thinking about the sine function. Oh, sines always starts at the equilibrium. Then it goes to a max. Then it goes back to an equilibrium, goes down to a min, and then finally back up to an equilibrium. That's sort of the thought process that goes in my mind when I think of sine. Similarly, for cosine, what is the pattern for cosine? It starts off at a maximum, goes down to an equilibrium, minimum, equilibrium, maximum. So that's the pattern that goes through my mind. Maximum, equilibrium, minimum, equilibrium, maximum. So when it comes to sketching, we need to find these special points. Now, it's going to be very difficult, especially if your period changes, but we're going to exploit one particular aspect. These critical points, these special values, whatever you want to call them, take a look at their x values. Notice they're equally spaced. Right? This length here is the same as this length here, is the same as this length here, is the same as this length here. So these critical values in terms of x's are always equally spaced. So if we know what the period is, we can easily chop up the period to figure out what these x values are. I think this will be a lot easier to understand if we just go ahead and do a handful of examples. So let's just jump right out of the gate. Let's sketch a, quote, complicated looking function. So let's sketch y equals 3 sine of 2 times the quantity x minus pi fourths minus 2. That seems like very, very intimidating, but I promise you it is super duper simple. The first thing I would do is I would start labeling things like crazy. And again, I said the easiest things to figure out is the amplitude and the principal axis. So clearly, right away, I hope everyone can see that the amplitude is 3. That means it's going to go up 3 and down 3. And the principal axis of the equilibrium line is y equals -2. It'll always be y equals whatever that guy is. The next easy thing to figure out is the phase shift. Right, so just by normal function transformations, we have an x minus, so everyone should know that goes to the right by pi halves. This right here will probably be the more, not difficult, but the more important one. Anything that's multiplying the x will affect the period, and the relationship is 2 pi over whatever that number is. So that equals pi. So what, I hear? Well, notice in a regular parent function with no bells and whistles, it takes 2 pi radians to complete the picture. What this math says is it only takes 1 pi to complete the picture. So it's as if this guy here got shrunk down into here. it takes 1 full pi. So notice that it sort of changes the range or the interval that I'm going to look at. I call this my quote viewing window. So my viewing window what is the interval that I need to see a full picture instead of being 0 to 2 pi, because that's what it is normally, right? I need to start at 0 and go all the way to 2 pi to see the whole picture. According to this math, I only need to start at 0 and go all the way to pi. So if I look at these x values, these are the x values I need to see one full cycle. But of course, we had a phase shift, right? According to our function, we have a right by pi. Why did I put a half? It should be pi fourths. We have a right by pi fourths. So what you have to do is just shift these guys here to the right. Now, we know about the number line, right? When things when things go to the right, it's positive. When things go to the left, it's negative. So shifting these numbers to the right by pi fourths is just adding by pi fourths. So add pi fourths to both endpoints, and we're going to get pi fourths, comma, 5 pi fourths. That is my what I call a complete viewing window. Well, what did we do? We found the x value where the where the pattern should start. We found the x values where the pattern should end. Our job now is to figure out what these inner x values are. Well, since we know that they're always equally spaced, right, we just need to chop up this interval into equal 4 pieces. The easiest way I do that is by taking averages. So I'm going to make an xy table, a horizontal xy table. And I know I need 5 critical values, so I'm going to make 5 columns. And I already know my interval, my starting and the final. I know my starting is at pi fourths, and I know that my final is at 5 pi fourths. And to figure out all these pieces, I'm going to take the average. So to figure out what goes here, I'm going to take the averages of these guys. So this work here, so here's scratch work. To find the averages of two numbers, you simply add them up and then divide by 2. So that's 6 over 4 divided by 2, which is 3 over 4. So it's 3 pi fourths. To figure out this guy here, you're just going to take the averages of these two guys. So for this position, I'm going to take the average of pi fourths plus 3 pi fourths all over 2. So I hope you guys get the idea of finding these new x values are very, very easy. You just have to take the averages of the two numbers that are besides it. So this is going to be pi halves. And then to figure out, I'm running out of colors. I'll just do this guy here. To figure out this guy, I need to figure out the averages of these two. So to figure out this color, I need to do the averages of 3 pi fourths, 5 pi fourths, all over 2. So that's going to be 1 full pi. So there we have it. We have our special values. Now for the y values, we just need to repeat this pattern, and we need to know that the pattern of the sine, or you don't even have to memorize this, you just have to know the basic shape. Oh, I know it starts in the equilibrium, then goes up, then goes down, so on and so forth. So then the shape is equilibrium, max, equilibrium, min, equilibrium. And then all I got to do is fill in the numbers. I find it easier to fill in the equilibrium numbers first. So we know that the equilibrium is at -2. That's what this guy says. So we have -2 here, -2 here, -2 here. Now remember, the max and min are always separated by an amplitude. And in this case, our amplitude is 3. So the maximum will go up away from the equilibrium, and the minimum will go down from the equilibrium. Well, if the amplitude is 3 and the equilibrium is -2, if I go 3 spaces up from -2, I'm at a +1. If I go 3 spaces down from -2, I'm at a -5. There we have it. Everything we need to do a pretty decent sketch of the sine function. So we'll go ahead and just draw a little trig axes. And again, since it's a sketch, I'm not going to be very nitpicky about, oh no, I'm going to break out a rule. That's not exactly pi fourths. Just label it somewhere that is reasonable. So don't put positive pi fourths here. That'd be obviously wrong. So I'm going to say, you know what? I'm going to squint my eyes, eyeball it. This looks like a pi fourths here. The next should be pi halves. The next should be 3 pi fourths. The next should be pi. The next should be 5 pi fourths. And then just go ahead and label your y-axis. It looks like I'm going to need a lot of negatives, so I guess I should probably extend this down. So we have a maximum of 1 and a minimum of -5. So here's -1, -2, -3, -4, -5. Right. So I need an equilibrium at -2. What I would do first is draw my equilibrium line. So I just like to just do a dotted line. Here's my equilibrium line. And then just go ahead and plot your equilibriums max, equilibriums min, so on and so forth. So I know at pi fourths, I'm at an equilibrium. At pi halves, I'm at a maximum. At 3 pi fourths, I'm at an equilibrium. At pi, I'm a minimum. And at 5 pi fourths, I'm at an equilibrium. There is our up and down wave. Right. Now, the instructions that I'm going to ask is just for one period. Obviously, if I wanted like a full, like more cycles, you can just continue on with the pattern. But I'm only just going to ask you for one full period. So this right here is all that I'll be looking for. Oops, too much. There you go. That right there is all I'll be looking for. Do you have the right x values? Do you have the right y values? Do you have the right shape? Those are the 3 components I'm looking for. Let's do another one. I mean, like I said, it sounds like a whole chore. It sounds like a very complicated process. But once you get like 5 or 6 of these under your belts, you're going to find that it's a pretty smooth and simple task to produce a pretty decent. This is not half bad. I'm not an artist by any means, but it's a pretty decent sketch of the sine function. Let's do an example of a cosine function. Sketch y equals 2 cosine of 1/3 x plus pi plus 1. And again, the first thing I'll do is identify the pieces. So we have an amplitude of 2. We have a principal axis of y equals 1. We have a left by pi, and this affects the period. So the period is 2 pi over whatever that number is. In this case, it's 6 pi. Once I have the new period, I know my, quote, viewing window is going to change, right? So my viewing window, according to this math, says I need to start at 0, and I need to go all the way to 6 pi to see my whole picture. But I did have a phase shift of going to the left by pi. So going to the left is subtraction. So if you subtract pi from each endpoint, that means my viewing window is from -pi, comma, to 5 pi. Once I have my viewing window established, I can go ahead and chop them up into 5 equal pieces. So I'll make an XY table with 5 spaces. I know I'd start at -pi, end at 5 pi, and everything is just averages. So for the middle portion here, it's just the average of these two. So to do averages, you just add them up, divide by 2, so that gives you 2 pi. To figure out this space here, you just take the averages of these two. So add them up, divide by 2. So that's going to be pi over 2. And to get this spot here, we're going to take the averages of these two. 2 pi, oh, I don't mean parentheses there. 2 pi plus 5 pi all over 2, so that's 7 pi halves. Next, you just got to know what the pattern is. So since this is a positive cosine, I know a positive cosine looks something like this. So I know it's going to start off at the top, max, go down to equilibrium, keep going down to a minimum, going back up to an equilibrium, and going up to a max. So I didn't even need to scroll up to the parent function. If you just know the basic shape, oh, that's a positive cosine. Oh, this is a positive sine. You can sort of figure out the pattern. You don't need to memorize it if you know the shape. So now it's time to fill in the numbers. The equilibriums I usually start first. So the equilibrium is at 1. And since the amplitude is 2, the maximum will go up by 2 from 1. So 2 spaces up from 1 is 3. 2 spaces down from 1 is negative 1. There we go. That is all the real work that you need to do. The rest is just plotting points. So if you can get up to this part here, I would be very, very happy. So then you should go ahead and make your trig coordinate grid. I have a lot of positives. I'm going to try to make more positives than negatives. That seems decent enough. And I do have a negative pi, so negative pi is somewhere on the left. Then I have a pi halves, which is somewhere halfway to the right. And then you just basically just try to equally space things. Again, I'm not going to break out a ruler and say, oh no, that's not equally spaced. But the more accurate and more equally spaced you make it, the better the graphs will look. So then so I need a 1, 2, 3, and I need a negative 1. My principal axis, my equilibrium, is at 1. And then just fill in the spaces, fill in the special points. At negative pi, I'm going to max at 3. At pi halves, I'm at equilibrium. 2 pi, I'm at a minimum. 7 pi halves, equilibrium. 5 pi halves at a maximum. So, and then just do your best to make a wavy-like shape. Right? For cosines, I sort of like to do these little tails here. There we go. To indicate that it is a maximum, so you have to actually like curl down. It would be wrong to just keep going up. This would be really, really wrong. These guys are maximums here. So everything else, back. There. So everything else should curl down from that point. So I like to put these little tails there. There you go. That is the shape of a cosine. So if you think you have it, I mean, that's basically it. I did prepare 2 more examples, and the other 2 examples are just what happens when there are reflections. So if you're all set and you feel good, feel free to get started, but I would suggest we look at some examples of reflections. So here, I want to sketch y equals negative sine of pi halves x plus 3 minus 3. So let's go ahead and identify the pieces. So we have an amplitude of 1, but it's going to be flipped as well. We have a principal axis of y equals 3. We have a left 3. And our new period is 2 pi divided by that number, which is going to give us a 4. So in this case, our viewing windows are whole numbers. It doesn't have pi's in it, and that's totally okay. So the new viewing window is from 0 to my period, but I went left 3, which means my new viewing window is negative 3 and 1. Make your XY table. I know I'm going to have 5 pieces. Starting at negative 3 and 1. And then just take the averages. So right in the middle, it's the average of negative 3 and 1. So negative 3 plus 1 divided by 2 is going to be a negative 1. This guy here would be a negative 2. This guy here will be a 0. I did that fairly quickly, but I think you guys can do averages. Now, what is the pattern? Well, the normal, so I'll go ahead and do this. This would be the normal sine function, sine pattern, would be what? It would be equilibrium max, equilibrium min, equilibrium. But we had things flipped. So the real pattern, the pattern that we should draw, is the flip pattern. So what changes when things flip? Well, when you flip things, the equilibriums will always stay equilibriums. That's the only that's nice. When you flip things, max becomes mins and mins becomes max. So at the max part, it's actually a min, and the min part, it's actually a max. So you don't. It's easy to figure out when you have reflections. Just flip your maxes and mins. Your equilibriums will always stay the same. Forgot the numbers. So what are the actual numbers? So my principal axis is at -3. So this guy here is a -3, -3, -3. And my amplitude is a 1. So the minimum will go down by 1, the maximum will go up by 1. So there we have it. Just make your trig graph. So let's see, I need some positive and negative x's, but I don't need any positive y's, so I'll just make it all on the bottom here. Something like that. So then just go ahead and make your tick marks. This one I don't need, I can actually just draw regular tick marks because they're all just regular integers. So we have -3, -2, -1, 0, 1. And my y values, we have -2, -3, -4. Principal axis at -3. And we'll go ahead and draw the pattern. At -3, it's equilibrium. At -2, it's a minimum. At -1, it's an equilibrium. At 0, it's a maximum. At 1, it's an equilibrium. So you can see it is our upside down wave-like pattern. Okay. So that's the only thing that happens when you flip things. When you flip things, the max and min, they flip-flop. Of course, the idea will be the same for cosine. So that's it. That is 5.4. That's all I'm going to be asking you to do. Can you produce decent, just one period of any sine or cosine function I give you? Have at it.